So today we're talking about spring. Okay, so basically mechanical spring. So spring terminologies, it looks very much like a screw. Okay, so it has basically helical kind of curvatures like that, and it has a pitch. So the pitch is defined as the distance between two adjacent coils. Okay, so if you take the center from here, and I should run that. So if you take the center over here and then the center over here, okay, so that's what you get, basically the pitch. Okay, just like the pitch for screw threads, right? Yeah. And you have this so-called wire diameter. Basically, this guy here, right? This is the wire diameter. Okay, yeah. It depends on material. Then you also have this mean coil diameter. So that diameter is the diameter between this center to this center here. So that's the mean coil diameter. Okay, yeah. And from here to here, basically from one side to the other side. So sometimes we call that outside diameter, OD, right? Yeah. So if I tell you the OD, and also you know the D, small d, then you should be able to calculate the capital D, right? Yeah, so those things. Helix angle, so that's not very important actually. So basically it's this angle at here, okay? Yeah, it depends on how the coil is twisted. Total number of coil, this is very important, okay? You need to be able to count the total number of coil. So that's pretty easy. So how do you count? You basically start from one end and you go one turn, that's one turn, right? And then you go another one, another turn. So basically you should count, like for example here, how many number of turns here? You have 1, 2, 3, 4, 5, 6, 7, and 7.5, right? Yeah. So that's how if I give you basically a spring, I probably won't tell you how many number of coils is in it, right? And a lot of most of the calculation, as you see, it actually starts with this number, NT. So you need to count how many number of coil properly. So let me repeat again, okay, because every time I see you give me so many different number of coils. You need to be able to count. Give you this one here. How do you basically count the number of coils? Okay, yeah. So NT, okay, know how to count. Okay, yeah. And then, okay, and I'll show you basically next is there are different endings for the coil. We use 0, 1, 2 to represent the different endings. So basically 0 will be the plain type of coil like this, so nothing really down to the end of the end coil, so that's just plain ending. And 1 and 0 are referred to the square or grounded type of coil. Okay, yeah. So remember this: there is different type of ending. Yeah.
So OD is little d plus big D, or is it big D plus 2 little d?
OD should be the big D plus small d.
There's 1D or 2D? 2 small d.
Should be big D plus small d, right?
Okay.
Yeah. Okay. So there are different ending. Now, because of different ending, then we have this so-called different number of active coil. So, for example, if this is a plain ending, then the active coil Na will be the same as the total number of coil Nt, right? Yeah. But if the ending is squared or grounded, then the Na will be different from Nt. And how we figure that out? We have a figure. I'll show you basically how to figure out the relationship between these two here. Okay. But that's the thing that you need to bear in mind when I give you a spring. And you read it says the spring is square and grounded, right? Then what jumps into mind is, okay, so what will be the proper value for the Na? Okay, based on your counting of Nt. That make sense? I'll show you an example later. Okay? Yeah. Free length LO is basically before you apply any force, how long it is. That's your LO here, right? That's the free length. Okay. Free length often in time can be calculated pretty easily based on, let's say if it's a plain one, it's actually pretty simple. For example, all your calculation is you count the pitch, right, and then plus the diameters of the wire. So generally you can get the value even without looking at the tables or things like that. Okay, but the LO, we should also refer to the table I'll show you next, okay, to calculate this. Solid length is basically the length when you fully compress everything, so everything is closed, and that length is the LS. Okay, so that basically the maximum deflection a spring can have, and then that's your LS, right? Yeah, so fully closed. Okay, so how do we calculate each one of this? Is the table 10-1. Okay, that's the source that you need to resort to get all the information. Okay, as you can see, table 10-1, there it says 4 different kind of spring endings: plane and ground, square and closed, and squared and ground. So what are they basically? So this is a plane. I showed you in the top there. There's nothing down to the ending of the coil. Square basically means you close the last turn of the coil with the adjacent ones here. So there's this guy here, right? You basically like press it down here instead of there's a tilting, right? So that's the square here. And the square is basically will be this guy here, right? Will be this one. Okay, yeah. Then you can also have so-called ground. So basically, if this is a plane right here, you cut off the top piece here, make it flat, okay, and basically flatten the top. That basically becomes the ground here, and that's this guy here. Okay, the second column. Okay, that's ground. Ground and square essentially is the square, and then you flatten up this top portion here, and that's become the ground and square. Okay, yeah. So when you read the question, you read it carefully, see what kind of spring you're dealing with, and then you look at the corresponding column here to find the proper formula. Say for example, right? You look at this guy here. Total number of coils NT, and if it's squared and grounded, then NT equal to NA plus 2, right? So if you count the number of coil, you get NT, then the NA should be what? NT minus 2, right? So that's how you get NA, okay? Because when you need an NA number for calculus stiffness, okay? And for free length LOLS, you have the formulas corresponding to different endings, right? So that's how you can calculate the LO and the LS, and also the pitch. Okay, yeah. So use this table to for your purpose, right? Yeah. Where's my? Oh, right here. Yeah. So you look at this guy here. So this is a picture taken from the internet here. Oh yeah. The other thing is, what we're going to deal with is all helical compressive type of spring. Okay. Yeah. For this lecture. So we're not dealing with any helical tension spring or torsional type of spring. So if you look at this picture here, can you tell me what type of ending this spring is? It's ground squared. That's right. Right? Yeah. So if I give you a spring, give you a drawing, and without even telling you what kind of ending for the spring is, you actually should be able to tell from this, and then you go to the corresponding column to find the proper information. Okay? Yeah. So let's say this guy here, right? This is a plane here. So let's say quick example right here. Maybe this is too soon. Let's to save some time here. Let's take a look at this one here. Okay, this is a square right here. Okay, and I know the pitch is 5 millimeter, and the D is 3 millimeter. Okay, so let's see how do I get the necessary information here. First, how many number of turns does it have? The total number of turns. NT is the total number of turns. Can you do a quick count of the total number of turns for this spring? How many? 7? 8?
8.
It's 8. So why is 8? It's from here, right? Up to this. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Is that good? So that's NT is 8. Now it's a square, so then what will be the NA? So you look at the table right here. It's a square, basically it's this guy here, right? So the NA should be 8 minus 2 equal to 6, right? So that's the active number coil. So what does active number coil mean? Essentially, when it's squared or closed, and that last coil basically doesn't have the capability of doing this deflection anymore, right? So active number coil is the total number of coil that can do this flexibility, give you the stiffness essentially. Okay, yeah. Then the LO, the total free length, according to the formula, it's PNA plus 3D. Okay, so you have P, you have a D, you have an NA now. So you plug in the number, you get 39 millimeter. LS is the solid length, and that's D NT plus 1, and now you get 27 millimeter. Okay, so this is the idea, basically, that you will very probably you will have to deal with. Okay, yeah.
So you ever have like a scenario where you have 2 different endings of the spring?
Yeah, you could. Yeah. So there are variable pitch, basically, right? Different kind of spring, but let's just focus on the normal ones here. Yeah. Okay, so now we understand it. Now let's look at the stress, right? In spring. Okay, let's look at stress in spring, and then we'll look at the strengths for the spring, and basically we'll go from the analysis or design from there. So if you cut a spring, okay, look at the cross section here, right? Then the free body diagram basically tells us is if this is a loading F here, then you have a shear force at here, then you have a moment generated by the F at here. So the moment or the torque is equal to F times half of the mean diameter, capital D, right? So that's what the spring here will feel here. So the F will give you the direct shear. So basically there is this direct shear. And the direct shear, let's call it tau D here, is F over the area. And area, you know the diameter of the wire, so it's 4F over pi D square. That's due to this F. And due to the torsion T, so you have this torsional shear. So this shear is, let's say, tau S, okay. Maybe tau T, I call it tau T here, is TR over J, right? It's TR over J, okay? T is F over cap D over 2, and R is small d over 2. And J, this is a circular one, so J is pi D to the power 4 over 32, okay? Yeah, so you calculate this, you get 8 FD over pi D cube. Yeah. So there are 2 different shear stress on the cross section. Then the total shear stress is the addition of these 2 together. So basically your combined shear is 8FD over pi D cube plus 4F over pi D square, right? Yeah. Okay. So that's this is a theoretical shear stress on the cross section. And what we can do is we can define ourselves, let's say we define ourselves so-called spring index C equal to capital D over small d. So this guy here is called spring index. Okay. Yeah. And we can also define ourselves another factor called Ks equal to 2c plus 1 over 2c. Okay? Yeah. So this one here, we call that shear stress correction factor. Okay? So based on this definition for C and also definition for the Ks, then this tau, we can rewrite the tau to be like this now. Ks times 8fd over pi d cubed. Okay? Yeah. So it can be rewritten like this. So this is basically the basic equation for shear stress in the spring material. Okay? Yeah. However, we're not going to use this actually. Okay? We'll use this under certain circumstances, which is basically after the set removal here. What we use is we have to take a look at the actual condition here. So when we derive this formula, we're considering basically it's a situation as a straight, basically a straight bar under torsion. But the spring is not a straight bar; it's actually a curved material, right? It's a curved object. For curved object under torsion, the experiment shows that the shear stress actually is larger at inner curve than the outside there. Okay? Yeah. So basically, there should be a compensation at here in terms of the theoretical value. So what we do is there's this guy called Bergstrasser. So he came up with experimental results here. So the tau, instead of this is a Ks, okay, we use a different factor here called a Kb. Okay, so this Kb is named after this Bergstrasser factor called Bergstrasser factor. Okay, and the Kb is defined as 4c plus 2 over 4c minus 3. Okay, so we will actually use this one here, okay, for calculating the stress, okay, in the spring material. Okay, so basically this one here predicts the largest shear stress, okay, at this inside curvature at here. Okay. Yeah. Okay, so that's a stress now. So now let's look at the strains, right? Well, actually, before we look at the strains, we need one more here. So now let's look at the other one called, let's look at the force and deflection. Okay, yeah. So basically what we're trying to nail down is what is the stiffness of the spring here? Okay, what's the stiffness? You need to, if you're really interested, you can look at my lecture notes. Actually, in your fourth year, you'll learn mechanics of material 2. So then there's a theory called Castigliano's theory. Okay. Okay. We can use this theorem to derive the stiffness, okay, of this the spring here. So from this theorem, we can get that y, okay, which is the deflection, equal to 8f d capital D cube Na over d to the power 4 times g. Okay, so this essentially is the force deflection relationship. Okay, force deflection relationship. Capital D again is the mean diameter of the coil, and g at here is the shear modular, right? So you can look up at the table to find this value. Now this is got to be careful. When you use this formula, this is Na. Remember what Na is? So we had when we talk about the coil, there are two parameters. One is Nt, there's Na. Nt is the total number of coil. Na is the total number of active coil, right? Yeah. So you can't use anything other than Na at here, okay? Yeah, because that's where I see a lot of mistakes happens. So then K equal to F over Y. So then K can be derived from this formula So that's equal to d to the power 4 over g and 8 d cubed divided by na. Okay, so that's how you can get the stiffness of the spring. Okay, yeah. So that's this part here. Now let's look at the strengths. Okay, the strengths. There are many different kind of material that you can use for spring. If you look at table, basically, if you look at table 10-7, table 10-3, okay, this table gives many materials. Okay, many materials. Some kind of call this, for example, music wire. You know, you use it for guitars, right, or violins. There's oil tamper wire, hard drawn wire, chrome vanadium wire, and then chrome silicon different wire. Okay, so take a look at that. The table. Okay, yeah. Now, what we're interested in is strengths. So let's look at tensile strengths. Okay, first. Okay, yeah. It is the strengths actually, it varies significantly with the wire size. Okay, and here's a table that you can see essentially shows you the relationship between the tensile strength and the diameter of the wire. Okay, yeah. So very interesting. You can see the smaller the wire, right? Actually, the higher value of this tensile strength. Okay, yeah. But overall, it satisfies a straight line if you use the log-log scale. So the SUT equal to A over D to the power of M, right? Okay, that's basically the formula here. So then what is the A, what is M then, right? D is of the wire diameter. A and M are from table 10-4. Okay, so A and M, they are from 10-4. So if you look at this table 10-4 here, if we're talking music wire, then the M is this much, and then for this many of range of diameter, and the A, there are two different units here, right? And A is, so A is this guy here, so KSI times inch to the power of M, okay, like this. That's how you find your A and M, okay? Yeah. But if you look at the stress in the spring, what kind of stress? It's a shear stress, right? It's shear stress. So if I'm going to compare the strength with the shear with the stress, I don't need the SUT. What I need is what? I need the shear strength. Okay? Yeah. So more precisely, it should be the torsional shear stress. Okay? So we call that SSY. So we need this guy here. Okay? Yeah. So how do we find SSY then? You find this SSY from table 10-6. Okay, from 10-6. So this is a 10-6 out here. There are two columns. Okay, so be careful which column you pick. First column, it says before set removed, and the other one is after set removed. And then the first column here is different materials, right? So what does it mean by set removed, before set removed, after set removed? So set removed basically means is when you have a spring, one of the common phenomena you see is you have a car. If you ran for a long time, so what happened? The car becomes what? Softer, right? Yeah. So basically, if you compress the spring for a little bit long time, okay, and when you let it go, so the spring doesn't necessarily go back to its original length anymore, right? So that's called a permanent set. Okay, yeah. Sometimes we don't want that to happen. Then what do we do? So the manufacturer will do this so-called process called set removal. So the set removal essentially, if this is your desired free length, so they actually manufacture let's say 30% more than your desired length. Then it'll subject the spring to fully closed, basically a load, okay, and then let it go for after a while. Then once you let it go, it'll go to your desired free length. See, because your maximum deflection cannot go beyond the closed condition, right? So that means basically the permanent set condition is removed, right? So that's called set removal, okay? Before set removal here, meaning you don't do any of that process here. So this column here, sometimes we call that just as wound, okay? So generally, we'll deal with this column here, okay? Yeah. If the question says, I have as wound spring, so you should look at this column for the material property, okay? Yeah. How do we use this table then, right? It has, so for example, if we're talking a musical wire, so this is basically means SSY for, let's say for example, for musical wire, okay? Then SSY will equal to 0.57 times SUT, okay? That's how you use it, okay? You find your SSY. Okay, so is that good? Okay, so now we're ready to take a look at an example for static analysis. Okay, yeah. So let's look at an example here. So I'll deal with ideal spring. So we basically, there are two kind of situations. One is ideal spring, the other is non-ideal spring. So what is ideal spring? Ideal spring basically means you think of the spring has a linear relationship between F and Y, all the way from open to close, right? But actually, in general, the starting 15% to the end and end 50%, they are not really linear. They are actually non-linear. So the curve probably looks like this, right? So there is a portion of a curve here, and then there's a linear portion here, right? Yeah. So, but if I say it's a linear spring, so basically we're saying it's a straight line from opening to the end. Okay? Yeah. So let's say we deal with the ideal spring here, and the spring has material property is a music wire. Okay, and small d is 0.006 inch. Outer diameter, okay, 0.036. And spring is square and grounded. Okay, square and ground-ended. Let's see. Okay, so free length LO, okay, equal to 0.63 inch. NT 40. So the question actually is simple because it tells you the most important parameter already, right? Okay, yeah. We'll assume a safety factor NT equal to NT. Safety factor NS equal to 1.2. Okay. So here comes the question: is it solid safe? Okay. Solid safe basically means if you completely close it, is it safe to close it basically? Okay. Yeah. Because that's where you have the maximum deflection, and that's going to be the maximum force, right? Yeah. And then maximum loading, maximum shear stress. Okay. So here's how you can solve it here. We find, okay. So we need the strength property. So SUT equal to A over D to the power of M. So I need to know what the A is and what the M is. So if I go back to my table 10-4, okay. So A, the unit we're using is inch. So we should use this column here for the A and this column here for the M. So M is 0.145, A is 201. Okay. Yeah. What's coming out of here, the unit is KSI. Okay? 422.1 KSI. That's SUT. Then we need SSY, the shear stress. So the shear stress is from table 10-6. Okay, so this is the table 10-4, 10-6. So this is a 0.45 SUT. Okay. So 189.9 KSI. Okay, that's SSI. Okay. Now we need to calculate the stress, shear stress in the spring there, right? Yeah. So the shear stress formula is which one? Is that this one here? We're going to make use of. Okay. Yeah, we may use this one. So what do we need from that formula? We need to know how much force we have, right? We need to know the spring index here. Okay, so first, let's see, the capital D is equal to the outer diameter minus the small d. So that gives us 0.03 inch. Then the spring index equal to capital D over small d equal to 5. Okay. In the formula for the shear stress, you have the Bergen-Strasser factor, the Kb. The Kb equal to 4c plus 2 equal to 4c minus 3. So c is known, plug it in, you get this much for the Kb. Okay, yeah. So then, what else do we need? Maybe I'll write down the tau here. So the tau equal to Kb 8fd over pi d cubed. So we need to know the F, right? The F here, the force. F equal to the spring stiffness times the total deflection. So what would be the spring stiffness? Spring stiffness formula, if you look at the formula, that's this guy here. So that require the total number of active coil, right? Yeah. So we need to know what the NA is. NT is a given, 40. And the spring says it's square and ground ended. So which means what? NA equal to NT minus 2 from the table 10-1. So which is 38. Okay. Then from the table 10-1, you can figure out the total LS, which is the solid length. So you see the solid length LS for square and grounded is DNT, right? It's DNT. So the solid length is LS equal to DNT. So why do we need the solid length? Because we have the free length. Then once we have the solid length, then we can subtract each other to get what? The total deflection. Okay? So the total deflection would be y, let's say delta y equal to LO minus LS, and that's 0.63 minus 0.24, okay, 0.39, okay, inch. Okay, so that's delta 1. And the last, we need the spring stiffness K. Spring stiffness K equal to this formula. Okay, so we already have NA, we already have a small d and a capital D. The only one is the capital G, the shear modular, or the modular of rigidity. So the G should be coming from table 10-5. So I don't have this one here, but if you look at the 10-5, and look for proper material, and you'll find the G value. Okay, so the G value you find that is equal to 12 megapsi. So plug it into here, all the numbers, Na38. So you get to K. Okay, so pound force per inch. Okay, yeah. Okay, so now you got a K, you have this deflection, then your total loading F, right, is equal to K times the delta Y, and it's approximately 0.74 pound force. Okay. Yeah, they say we need to be pretty small, right? But because your wires D is very small, so the shear stress generated is actually not that small. Okay, it's pretty big. So then plug it into the shear stress formula tau. So we get 338.2 psi. Okay, so that's the shear stress. So the question come back is it solid safe? What do? We compare this tau, the actual shear stress, with which one? Exactly, right? So apparently you see one is 200, one is 300, so it's bigger than that. And our safety factor is actually 1.2, so not even close, right? Yeah. So basically your tau is bigger than this, so which means not solid safe. So you can't press it completely closed. Okay. If it can't, then the concrete question is, so then what can we do then, right, to make it a solid safe? Okay. So then in terms of design, basically what you can do is there's different ways you can do. You can probably have a different wire, small d, or you can have a different mean diameter, capital D. Or you can also do is to have a different free length. Okay, different free lengths. Yeah. Maybe you can take a guess here. If I'm going to redesign a free length, would it be shorter or longer now? Huh? Shorter, huh? Yeah. So what will be the free length, a proper free length? Okay, so let's do this. The proper free length basically is let's say ys equal to what, right? Let's say delta, I'll call it delta y. Okay, so let's call it delta ys equal to what, essentially. Okay, yeah. You have your SSY. You have your safety factor NS. So when you use this one divided by your NS, this one gives us this so-called basically allowable shear stress, right? This is the allowable shear stress in the spring, okay, in the spring. And you know that the shear stress calculation is based on the formula of KB and K times F. And KB 8 times F. F is the spring stiffness times the deflection, right? The deflection. So we can't have the same deflection as before, so we basically need to figure out what will be a proper deflection here, total deflection. So then divided by this, right? Yeah. You have this, then this no. Everything you know except the delta ys. So you can calculate delta ys based on this formula here. You get 0.182 inch. Okay, 182 inch. So this value basically is the maximum deflection that you can have based on the allowable shear stress, right? Yeah. If this is the maximum shear maximum deflection you can have, then the suggested free length, right, is basically the solid length plus this guy here, right? The solid length plus this. So let's call it LO prime now, not the original LO anymore. So this one turned out to be 0.422 inch. And what's the original free length? 0.63, right? Yeah. So that's the kind of typical questions that you probably will see. All right? Yeah. Any questions? All good? All right. See you Friday. Last point. Do the evaluation. Okay, good.